Okay, so we're in experiment view for our smoke tests. Let's dive in. So that we've run a single smoke test just to verify that everything is being logged from our experiments and that we can fit the data in some way. So we've taken a very small fraction of the data, about 1% of the data set, and try to fit a model using the default parameters of the model. And the goal is to verify if our model can even overfit this data. Because if we fit the data, then we have to revisit our features, and there's no point in investing more time in the modeling phase. So let's dive into this experiment. So a few things we want to check are our metrics being logged. So it looks like the metrics are being logged. Let's create a empty view just so that we can quickly compare these metrics. So we're going to add a line chart. We'll change this to step and let's see. Yeah, so it looks like the model can fit the data. So you see our training loss is decreasing over time, while there's like no measurable change in our validation loss. In fact, as the model is overfitting, our validation loss keeps getting, but that's okay. We don't really care about optimizing for the validation loss. We just want to know, can this model fit the data, which it looks like it can. The next thing we are going to do is see if we logged all the things from our prediction pipeline correctly. So did we log our predictions data frame? So we logged our predictions data frame. It's a JSON file. And view this JSON. So each entry in this JSON, every field is a feature column, and the value is the value of that feature. So every entry is a single row. So we have about, as you can tell, these are the title embeddings from BERT. So it's about 773 features, along with other features such as the timestamp features. So the day of the week, and the year. And also, if I scroll all the way down, I should also have, there we go. I should also have my prediction, the target value, which is score, and the error, the computed error metrics. So the root mean squared error and the mean average percentage error. Cool. So let's move on to looking at these errors and investigating them in a panel. So I've already created a panel view for this experiment. I'm going to switch quickly to that view. So I'm going to use this Vega scatter plot. So the Vega scatter plot is a public panel that you can add to your project. It's a panel that's been built in Vega. Comet Panels supports any type of JavaScript library, so you can build your panels in Vega, plain JavaScript. And the goal of this panel is to create a scatter plot that we can use to debug our model predictions while still preserving information about the features. So let's take a look at this panel. So in the panel options, we specify a table file name. So the table file name is predictions.json. That's a prediction data frame that we logged in JSON. We also specify the features we want to analyze. So in this example, I'm not going to look at the individual title embedding features because there's just too many of them. So we're going to focus on a few, just a small subset. So we're going to look at the day of the week, the day, the month, the year, the score, which is the target variable, the root mean squared error, the mean absolute percentage error, and the predictions that our model made. And we're going to put these features on both the x-axis and the y-axis, so we can dynamically switch between them and see the relationships between these features and predictions and errors. The last thing I want to highlight in this panel is that you have tooltip options. So if I hover over a data point in the panel, you can see that it brings up additional information, and I can customize this to be whatever. The datum here refers to a single row in our data frame. So I can reference the column in that row by this suffix. So datum.score would be the score column, our MSE would be the root mean squared error, prediction would be the prediction. And so let's take a look at these predictions. So we look at the root mean squared error versus the score for this smoke test. So it looks like samples with a higher score have a much higher error. So if I hover over this, I see that a score of 770, model outputted a prediction of 28. So that means that the model is having difficulty with these outliers. So that's maybe something we want to take into account. Either we remove the outliers, add new features. There's a few options in front of us, but it's good to know what is the type of target variable that your model is having difficulty with. So let's switch now and compare the predictions that the model makes to our target variable. So the predictions over here, it looks like there's a whole bunch of predictions that were spread out. So for a single target variable, right? So the target variable is 2, I think in some cases it might be 1. Okay, yeah, score is 1, but then our model predicted an estimated score of 30. So that means that the model is like overestimating these low scoring posts. So what that sort of implies is that it's very difficult to differentiate between low scoring post and high scoring post. One of the things that we might want to do is maybe, this sort of implies we might need better features, because the model isn't able to differentiate using these like baseline features what a high scoring post looks like just primarily from that title embedding and the timestamp features that we've provided. So now that we're done with our smoke test, let's go check our learning curve experiments. So we go back to our smoke test view, and we'll jump in to our learning curve experiments. Actually, rather than use the smoke test view, I've already created a learning curve view that isolates just this subset of examples. So in this subset of examples, we can go to our panels, and I've created a panel that basically plots the validation root mean squared error as a function or versus the smoke test fraction parameter. So I was gradually increasing the fraction of the data set used to fit this model. And what we want to see is that does adding more data to the model actually help it learn? And we were expecting a decreasing curve, and we have that. Adding more data does help the model learn, but it looks like beyond a point, it just oscillates around this value of about 7, like somewhere around 74. So beyond 30% of our sample, adding more data doesn't seem to improve the model performance too much. So this is something that implies that maybe we need like better features. So that's something we might want to work on, because even if we were to add more and more samples here, it looks like this baseline set of parameters, hyperparameters, are not able to fit the features that we have. Okay, so the next thing we're going to go and look at in our experiments is the optimizer performance. So I prepared another view called the optimizer regression model view. So the optimizer regression model view is just the sweep that we've done with our LightGBM regressor and the optimizer. As you can see, we have a set of values for our root mean squared error and mean average percentage error. These are looking, at first glance, they look worse than our baseline. So clearly, like, this model is not good enough. So like running the sweep hasn't really found anything that can beat our baseline, which is just guessing a constant value. I believe like the constant value that we had, the root mean squared error was about like 68. Clearly, we need to revisit our feature engineering. And the sweep will tell us two things, right? Which parameter what we're trying to discern here from the sweep is what is the most important parameter in the sweep that affects our model. So we'll hop on over to the panels view. And I've set up a couple of panels here. I've set up the optimizer report, which is a featured panel. You can find it in the featured panel section. And this report tells us what are the most significant parameters here that affect the model's performance. So the learning rate seems to be the most significant parameter. It has a positive correlation. So that means that this can be a little tricky, because a positive correlation here means that decreasing the learning rate decreases the root mean squared error. The number of estimators is like our second most important parameter with a slight negative correlation. So that means that increasing the number of estimators decreases our root mean squared error. So you can see that if we sort these experiments, yeah. So the lowest root mean squared error, we had a small learning rate and a large number of estimators. So this is good, right? So it looks like changing the number of leaves in the tree isn't necessarily making a huge difference. What is making a difference is like increasing the number of estimators and keeping the learning rate fairly small. So this is good. This is information that we can use to iterate like on our modeling approach, right? Like we know that these are the parameters that sort of have very strong effect on performance. We can also look at this parallel coordinates chart, which gives you an idea of the distribution of hyperparameters versus the final validation metric. So the lowest validation metric here basically has the lowest number of leaves, the smallest loaning. It also has the lowest mean average percentage error, and the only difference is that the number of iterations is very high. So basically, we've narrowed down two of the parameters in our search that we know affect our performance, and now we don't necessarily have to waste our time playing around with the number of leaves. We can just focus on just increasing the number of iterations, and we know that we have a good chance of lowering the root mean squared error. So this is the approach you want to take when optimizing your parameters. Hopefully these tips were useful and that you've learned how to set up a smoke test, why a smoke test is important, how to run a learning curve experiment to verify if adding more data helps you solve your problem, and how to structure your hyperparameter search so you can fairly early on isolate parameters of interest that actually make a difference to your model performance. And so you don't really waste your compute budget on searching a space of parameters that might not necessarily help you achieve your modeling objective. Yeah, and that's it. Hopefully you enjoyed this session. Stay tuned for more.